I'll be talking today in this section about tuning the MPICH binding options on Aurora, specifically how to bind your processes to the CPU, to the GPUs, and how to appropriately bind to the memory regions. I said that on this agenda slide. The link here that goes over all of this stuff in more detail. So if you have access to the slides in the technical slides channel on Slack, you can just open it up and click on this link. So let's recap a little bit what you saw yesterday. So it's important to know your node topology and how the node is laid out. So on the Aurora nodes, as you saw in the picture of the nodes, and then this picture that's on the slide here, there are why is this going automatically? There are dual socket CPUs. That means there's 2 CPUs on the node, and each CPU houses 328 gigabyte QEC GPUs. You can see them with these red line connections right here, and then the same on the other side. These GPUs have all-to-all connection or all-to-all topology, so they're all connected to each other. And you can further partition these GPUs with the way the GPUs are architectured. Usually you can split the GPUs in 2. We call them tiles here at Argonne. There's also 2 different types of memory on each socket. So there's kind of the slower but higher capacity DDR5 memory. So there's 512 gigabytes attached to each socket there. So for a total of 1 terabyte of memory there. Then there's also some high bandwidth memory as well. So there's 64 gigabytes of high bandwidth memory per socket. Another important thing to keep in mind, so if your application is very communication heavy, you maybe need to be aware of how the network interfaces are handled. So there's 4 network interfaces or 4 NICs attached to each socket through a PCIe switch. And you see the same over here. And this can make for kind of awkward situations in terms of binding your processes to the cores, because there's 6 GPUs total, but 3 of them are attached to 1 socket, but there's 4 NICs. And a common configuration is, as I said, using a single tile in each of these GPUs. So that would mean there's essentially 6 effective GPUs that you're using, but only 4 NICs in order to send the communication out through. So that's something to keep in mind with your application. That might be a performance bottleneck for some people. So again, just to reiterate, on each socket, there's 3 GPUs and 1 tile per GPU. And the thing to note is we've disabled the first core on the nodes. They're reserved for the system processes that we have running on those, and you can't effectively bind to those cores. Another thing to note is for performance, we don't recommend trying to bind to hyperthreads. So don't try to bind to this, but you can always experiment with your own code. Maybe you'll get better performance binding to those hyperthreads. So how do you do this? How do you bind your processes to the cores? Well, in order to do this, we use MPICH in order to launch the processes on the node through MPICH. And there's a environment variable, or I'm sorry, there's a command line argument that's CPU bind list. And this allows you to explicitly bind the ranks to the various cores. So here we export this environment variable CPU bind scheme, where we set the command line argument CPU bind equals list, and then we explicitly tell it which cores we want to bind to. And so you can give it a range, or single cores, comma separated. And so the first rank here is going to be bound to cores 1 through 8, and then we put the colon separator. The second rank is going to be bound to cores 9 through 16. Third, 17 to 24, so on and so forth. And all these ones here that are marked in red, those first 6 ranks are being bound to the first socket. And then all these ones in blue, they're all being bound to the second socket. You notice that we start with 53 here instead of 52. We start with 1 here instead of 0, as I mentioned previously, because we reserve the first core in the sockets for system processes. So this is a common configuration that's used most often, where you bind 12 MPI ranks per node and 6 per socket, where each one of those ranks is also going to bind to one of the tiles on the GPU. Visualizing this, you can see here, so 1 through 8, just these blue squares binding to the first set of cores, first set of 7 cores, that's not the 0th core. And the orange is binding, it's the second rank, and so on and so forth. Now, in terms of how do you bind the GPUs, well, the main way to do this is you want to bind your GPUs and to the same cores or the same ranks that I'm sorry, I don't know why this keeps automatically playing. You want to bind the GPUs to the same socket that your ranks are bound on. So for socket 0, you want to bind GPU 0, 1, and 2, and then socket 1, you want to bind 3, 4, and 5. And the common way we do this is using device discovery by setting the ZE affinity mask, which masks which GPUs are visible to the cores. It's very similar to how CUDA visible devices work. And we have a script available in order to do this, as Thomas had mentioned and some others had mentioned previously. It's this GPU tile compact script, which is globally available on the compute nodes. And this automatically will handle the bindings for you to map the GPUs to the appropriate ranks based on the local rank. And the other pathway that I was going to mention was this GPU bind list. But that has some limitations, which we'll talk about in a few seconds here. So as we mentioned, we have this wrapper script that we designed to explicitly bind each tile to the MPI ranks by setting the ZE affinity mask. In order to use, see, there it goes. In order to use the script in your MPI exec, you would set the CPU binding scheme as we showed previously, and then just insert this GPU tile compact.sh just before your executable and your arguments. So what that will do is we'll map rank 0 to GPU 0 tile 0, rank 1 to GPU 0 tile 1, and so on and so forth, all the way up through to rank 11. And if you have more than 12 ranks, then it round robins. So rank 12 on the same node would be GPU 0 tile 0. Now to bind explicitly using this GPU bind list, it's very similar to the CPU bind list command line argument to MPI exec, where here you explicitly say which GPU and tile you want to bind to. So GPU 0 tile 0, then separate by a colon here, then GPU 0.1. So that'll bind rank 1 to the GPU 0 tile 1, then colon GPU 1 and tile 0. That'll bind the next rank, and so on and so forth. And then you would just insert that command line argument into your MPI exec command. So as I mentioned, there's some limitations. You need ZE flat device hierarchy set to composite, which is the default option on Aurora. And it won't work if you change the device hierarchy to flat. So for example, if you load the frameworks module, this changes the device hierarchy to flat. So using this scheme wouldn't work in that situation. So another important consideration is the different memory regions or different memory options available on Aurora. So each Sapphire Rapid socket, as I said, has 512 gigabytes of DDR5 RAM, and there's also the 64 gigabytes of high bandwidth memory. And the optimal configuration would be to have each rank placed close to the memory that it'll be accessing. So if you have ranks bound to socket 0, you don't want to bind them to ranks in the opposite memory bank. So some advantages, obviously, the DDR5 has a lot more capacity, but it's slower. And the high bandwidth memory, HBM2E, is faster, but has limited capacity. There are also ways you can utilize both memory banks, but it's a more complex setup, and you have to use the NUMA library APIs in your application in order to do that. So how are these things arranged? Well, they're kind of arranged in the way you expect them to be. So each socket has different NUMA IDs, where ID 0 corresponds to the 512 memory region, so the DDR5 memory region, and for the first socket, or socket 0, I'm sorry, I did socket 1 and 2 instead of 0 and 1 here. And for the high bandwidth memory, it's not ID 1, so this might trip some people up. It's actually ID 2. So it first enumerates the DDR5 memory, and then it enumerates the high bandwidth memory. You can see that if you do NUMActl on this command here, you can see the NUMA 0 here has approximately 512 gigs of DDR or gigs of memory, and if you add these two up, and then node 1 has also approximately 512 gigabytes of memory. Then node 2, you can see, is that 64 gigabytes of high bandwidth memory, just by looking at the capacities at least. So how do you bind these the ranks to the different memory regions? Well, again, there's a command line argument for that. It's very similar, membind list, or you can just explicitly bind the ranks. So here we show the 12 rank example, where you just set those NUMA regions or NUMA IDs here in the colon separated list. You can do the same. So you can either bind directly to the DDR5, or you can bind to the high bandwidth memory, or you can do both. But if you do both, you need to ensure that your application is set up in order to utilize both memories by explicitly having calls to the NUMA library. So this won't work out of the box. You have to put some effort in order to do that. It's a more advanced case. So that's basically the short review on how to set the bindings. So here I show 12 rank examples, but there are obviously, that's not going to be the only way that people want to set it up on their machine or on their for their application. Another common one that people do is, as Marta was mentioning yesterday, is to use the CCS engines, or set the compute command streams in order to split the GPUs up even further. So you could split them up by 2. So there you would want 24 MPI ranks per node. So that would obviously change how you set up these bindings. Another common way is to split the CCS, to split the tiles up in 4, and that would have you use 48 ranks per node. So we have all these examples on how to set these bindings in those scenarios in our documentation pages. So if you want some more information on that, please encourage you to look at those. But that's all I have for now.